The Earth was formed about 4.5 billion years ago, and life appeared on the planet within the first billion years. Most scientists think that life evolved from the organic material that was present on the primitive Earth. So in this program, we're going to look first at the solar system and beyond for the kind of organic material that would have been on the Earth. And then we're going to consider some of the experiments that try to simulate the chemistry that led to the emergence of life. First, the organic material. Our search for organic matter begins in Sweden at the Onsala Space Observatory. To avoid the problems of the wind and sun, the telescope is housed in a ray dome, a giant golf ball of membrane which is transparent to millimeter waves, such as those from outer space. The telescope, built in 1976 and designed to search for molecules in interstellar clouds, is operated by Åke Hjalmarsson. We are going to track Orion A now. Okay. Orion A, which lies behind the nebula, is a giant molecular cloud 100,000 times as massive as our Sun. Inside the cloud, gravitational collapse is producing new stars, and some of the youngest have emerged to light up the nebula. Now we should check the coordinates. Yes, it seems to be all right. Okay. These mirrors switch the line of sight. Cloud, sky, cloud, sky. This subtracts the background radiation. Okay, it's a stronger signal, so we should see it now. In this observation, the telescope is tuned to an emission line of the molecule HCN. Okay. And HCN is just one of more than 20 organic molecules detected in Orion A. The gravitational collapse that we detect within the giant clouds is no different from the formation of our own Sun. At Kyoto University, a model of the formation of the solar system, the Kyoto model, is being developed. The dots represent planetesimals in a swirling fragment of cloud with angular momentum. Gravity draws the bodies towards the center to form a protostar, and eventually into a disk from which the planets form. Professor Chushiro Hayashi leads the Kyoto group. His model takes into account gravitational forces and random motions within the cloud, but ignores important magnetic fields. The inclusion of their effects is a task for the next generation. The most primitive material from the early solar nebula, brought to us by comets from beyond the outer planets, is being examined by Don Brownlee of the University of Washington in Seattle.
Annually, there's 10,000 tons of dust that falls to the surface of the Earth, which is about 1 10-micron particle per square meter per day. So I always like to say that if you're laying out in the sun for the day, you're probably hit by 1 cometary particle per day. Even though dust is everywhere around us, it's almost impossible to find because there's so much terrestrial dust that dilutes the extraterrestrial component. So it's really only easy to collect if you go very high in the atmosphere, up in the stratosphere.
At an altitude of 20 kilometers, we are almost in the blackness of space. Under the wing, this small perspex disk picks up, on average, 1 particle each hour. Particles as precious as this must not be contaminated by terrestrial dust. In the clean room, a dust particle is prepared for examination with a scanning electron microscope. single dust grain is magnified 16,000 times. From this picture of the grain, Don Brownlee can pick out one tiny crystal for analysis by X-ray fluorescence, a technique that tells us which elements are present in the crystal. The organic components of the dust grain can be identified, and they too can be eventually analyzed.
Some of the particles we think come from comets. And even though we don't know much about comets at the present time, it's likely that the closest into the sun that the comets could have formed was the region of Uranus, Neptune, and Pluto in the solar nebula, or further out, a very cold condition, a place where grains should have been quite well preserved from the state that they were in originally in the nebula. And of the dust particles, the different types of dust particles that we collect, one particular type is a very porous aggregate of grains about 0.2 or 0.3 microns in diameter, put together to form a sort of a porous cluster of grapes structure. We believe that the pores in the structure were originally filled with ice. But the grains themselves are made primarily of silicates, non-clay minerals, no water-containing silicates, and some sulfides also, and a large amount of amorphous or structureless non-crystalline carbon that just permeates the whole mixture. And there's a baffling array of sizes of mineral grains ranging from less than 1/100th of a micron in size up to larger than micron in size.
Our search for organic matter continues in a most unlikely place, Antarctica. Behind the hills lie sheets of ice scoured by the polar winds that remove the snow. The exposed ice surface may be up to 1 million years old. Any debris deposited since that time will be left lying here. And the debris that we find is another type of primitive material from the solar nebula.
Let's have a look at this hillside here. We haven't been down that far, so there's a lot of rocks up there. Let's just go up and kind of fan out and have a look at, see if there's any meteorites. Right out. May not be able to get apart.
This team of American scientists searching for meteorites is led by Bill Cassidy, a geologist from the University of Pittsburgh. Locating meteorites is not easy. On other continents, it is often difficult to distinguish a meteorite from any other chunk of rock. But out on the bare ice, almost anything you run across that is not ice is going to be a meteorite. The Antarctic environment is so cold, dry, and pollution-free that meteorites are preserved for great lengths of time and in a relatively uncontaminated state. The collectors take great care to keep them that way.
Nice little guy. Hey, yeah.
Well, we've been out 2 months now, and our total collection of meteorites is in this box. There they are. It's about 320 meteorite fragments there, and it's been a very successful season for us.
Only about 2% of meteorites contain a significant amount of organic matter, the carbonaceous chondrites. Once collected, some of the meteorites are analyzed back at the NASA Ames laboratories in California by Dr. Ted Bunch.
Set up for iron, calcium, magnesium on the map here, and we'll go for analysis.
Okay, it's about 10 seconds.
Okay, that's good. Right. Carbonaceous chondrite is a stony meteorite, essentially. that contains organic compounds. For example, amino acids, fatty acids, sugars, alcohols, aromatic hydrocarbons. In addition, some carbonaceous chondrites contain water up to 20%. And some also contain a proportion of volatile elements other than water that's equal to solar proportions. So it makes them quite interesting and necessary to study in order to see what was happening 4.5 billion years ago. The organic compounds, at least we think, some of the organic compounds, the simpler ones, probably condensed out of the early solar nebula and accreted onto a parent body. After some time, these organic compounds were probably altered by events that were happening to the parent body. For example, impacts that generated some heat, and ice that had melted due to some heat effect, whereby the water would travel through and alter the silicate materials into clays. And at the same time, this process would act as a catalyst so that the organic compounds would continue on into a more sophisticated form. In other words, organic synthesis.
Whereas Brownlee's cosmic dust is quite pristine, that's not true of meteorites. They provide material that has been mildly processed, chemically changed since the formation of the solar nebula. Some meteorites are aggregates of different kinds of material, and this raises the question of the origin of these substances. Investigating this is Dr. Colin Pillinger of the Open University.
Our particular excitement of studying meteorites is the fact that we can look beyond the solar system. When we discovered isotopic anomalies in meteorites in about 1973, then we knew that we had in fact remnants in meteorites that had survived the formation of the solar system.
Take a small amount of meteorite and heat it in a stepwise fashion. At each step, gas is evolved, the gas coming from the various types of grains that are in the aggregate of the meteorite. The isotopic abundances of the elements in the evolved gas can be measured using a mass spectrometer.
We've got stacks of gas. There's a lot of gas. A lot of gas. There's a lot of gas. That, perhaps this is the big one. We suddenly found that nitrogen, instead of being just a boring element with a very tiny isotopic variation, in extraterrestrial samples it shows one of the largest variations of any element. So you can have samples which are very enriched in nitrogen-14 and samples which are very enriched in nitrogen-15. And from these different signatures you can relate to many, many different nucleosynthetic processes. Here we go. Scanning now. 29 feet. Ooh! That is a lot of gas. The experiment which we're looking at now is to try and find probably the highest enrichment in nitrogen-15 that has ever been found in a meteorite. And it could very well be related to some kind of supernova synthesis. And if that is so, then maybe the iron that we're finding this heavy nitrogen in is a primitive form of iron. This is iron that condensed just at the time when the solar system was forming. It's not iron which has been through a kind of differentiation process during the formation of a planetary body. And that would make that iron extremely exciting. Oh! This is a cracker! You should see this one. Get the calculator out, Frankie, quick.
So isotopes tell us about the generations of stars that created the stuff of our solar system, as in this supernova explosion. Supernovae eventually blow the elements away into the interstellar medium, from which the solar system formed about 4.5 billion years ago.
4.5 billion-year-old smell.
released by grinding up a piece of carbonaceous chondrite. Professor David Deamer of the University of California has produced these cell-like structures by treating the organic material of the Murchison meteorite. Professor Deamer recognizes these from his studies of chemicals that form membranes. By taking organic molecules of the kind extracted from the meteorite and mixing them with an aqueous solution, he obtains similar structures. A simple experiment that simulates the interaction of a primitive ocean with primitive organic material. Under the microscope, we see vesicles which have membranes similar to those in living cells and microorganisms. So we can understand how material could have been organized into cell-like structures on the primitive Earth. 4.5 billion years ago, simple organic substances outgassed from the heating of stuff like the carbonaceous chondrites. But how could the complex molecules of life be produced from such simple substances? The answer probably lies in an experiment of the kind first performed in 1953 by Stanley Miller. Lightning discharge is simulated in a gaseous mixture similar to the Earth's primitive atmosphere. Performing this experiment at the University of Maryland is Professor Cyril Ponham-Peruma.
What is happening here now? How long has this experiment gone on?
Just now, 24 hours, so it's a time to stop it.
From these simple gases and the water that represents some primitive pond or ocean, a complex mixture of organic molecules is produced, a primordial soup.
In this experiment, we are recreating the conditions that happened on the primitive Earth about 4 billion years ago. And in a typical experiment, we can get the building blocks of the molecules that are necessary for life. In other words, the amino acids that go to make up a protein, the genes, or one might say the genetic bases that go to make up a nucleic acid molecule. And in our work so far, we've been able to establish very clearly that these components can be formed under what we describe as primitive Earth conditions.
After concentrating the organic products by evaporating the water, the mixture is analyzed by gas chromatography to identify the amino acids and other monomers that are the starting point for the larger molecules of life. But how can polymers such as polypeptides be produced?
Occasionally, we are able to fish out of this soup small fragments of those amino acids, those components linked up together to form a chain. So the next stage appears to have also taken place in an experiment of this type. Darwinian evolution began with the appearance of life. All the processes that went on before life began might be described as chemical evolution. And that's exactly what we are showing here. The components of the primitive atmosphere giving rise to the building blocks of life.
A chemical evolution that took millions of years, accelerated here by recycling and using a continuous discharge, producing primordial soup with all the molecules needed for life. But in nature, contained in a vessel that could have played a crucial role, the very rocks of the Earth. Introduce some of the missing ingredient, some powdered rock or clay, to our primordial soup, and the organic molecules are absorbed.
Well, clays are important in prebiotic chemistry because clays have concentrated a lot of the organic material. The prebiotic soup is considered to be a thin soup of organic matter. So clays have helped to concentrate on it. That is one role that clays could have played. Another one comes in the process of ordering molecules. Amino acids occur in a certain sequence. So a suggestion has been made that the clay was responsible for that ordering. So here we have two reasons to believe that clays must have played a role in the origins of life.
Putting these ideas together is Professor Jim Ferris of Rensselaer Institute, Troy, New York.
We're trying to work towards a synthesis of RNA, since the RNA we feel is the central molecule to prepare for the first living system. So if we can synthesize those on a clay surface, which can serve to concentrate and organize these units that go into RNA, we may have a very good system which may have taken place on the early Earth, where we might end up with a clay particle covered with RNA polymers.
We've got all the building blocks now. The next stage is when we are able to put this together and show that a process is taking place which can be recognized as what the biochemists call replication.
So when, in the 4.5 billion years of the Earth's history, did life emerge? Our search takes us to some of the oldest rocks, the Barberton Mountains of South Africa. Here are formations that are about 3.5 billion years old. Geologist Don Lowe of Louisiana State University and his colleagues are looking for fossils in the sedimentary rocks that were deposited in some ancient shallow sea.
Here's some of the stromatolites. Oh, yeah. These stromatolites look just like the ones we found up on Granville Grove.
Yes.
Out there. Yeah, you can see this mound shape. It's beautifully developed, but they're upside down.
It looks like the upper volcanic flow has just molded right into the top of the stromatolites.
This is Komatiite down
Yes.
here.
Stromatolites are fossilized mats of bacterial colonies interspersed with the rocky sediments. Further up the hill, Don Lowe is searching for a different kind of fossil in the oldest part of this rock formation. The dark bands in this silicate rock contain organic material.
Gary, there looks like some good banded shirt right here.
Fracture there now.
How does this look?
Oh, that'll make some nice slabs.
Yeah. Excellent. Laminations are very fine.
Yeah.
Okay.
Prepared as a thin section, the chert reveals the very earliest fossils yet discovered. Single cells about 20 microns in diameter. Also, a mesh of fossil filaments coming in and out of view as the microscope is focused through the section. From filaments like these, the bacterial mats are built. In a few rare places, we get a glimpse of what the primitive Earth might have looked like when the bacterial mats could have covered much of the surface. So this is our target if we are to understand how life emerged. We have the organic matter, and we know how, in some primeval pond, it could have been organized into the building blocks. The problem that remains is to understand how replication first occurred, how the chemistry came to life.